All right. Hi, everyone. Thank you so much for joining our session, and hope you're welcome, enjoying OSDS until now. So our session today is about Apache XTable and how it kind of enables interoperability between these lakehouse table formats that we have been talking about as an industry as well. So just to give a little bit of intro, and then we'll take it from there. My name is Dipankar. I'm currently a staff developer advocate here at Onehouse.ai. I focus on open source projects like Apache Hudi, Apache XTable. Previously, I've worked with Apache Iceberg and Apache Arrow ecosystem. In the previous life, worked in different like spectrum of the data pipeline, like data engineering, data science, data architecture in my last job as well. And yeah, that's pretty much about me. Ashwin, do you want to introduce yourself?
Yeah, sure. Hello, everyone. I'm Ashvin Agrawal. I'm a research engineer in Microsoft GSL Lab. And as part of my job, I engage with a lot of open source projects. Currently, I've been engaged with Xtable and Polaris. In the past, I've worked with Geode, Heron, HDFS, Yarn, and a couple of open source projects. I've also worked at VMware, Yahoo, and a startup which was acquired by Arista Networks. And I'm very happy to meet you all here.
Thank you so much, Ashwin. Yeah. All right. So in terms of the agenda, we will just start with the lakehouse table format background, just for the people who have been hearing things, but just want to get a like touch of it and basically understand the problem statement at the first time. And then we'll go to our main focal point, which is which format to choose, what are some of the considerations, and how Xtable as a open source project solves that particular problem. And we'll do a little bit of deep dive on the Xtable architecture as well. But obviously, we'll link some of the important documents as well for you guys to like look it up later. And finally, end up with some of the important learnings of putting Xtable in practice in production. That's what Ashwin is primarily going to cover today. So a little bit of history, and hope like for people who already have a background, it's kind of a refresher in a way. So over the years, organizations have been kind of investing heavily on building centralized and reliable data platform, right? So the whole idea was that if they could democratize data, it would allow data consumers in the pipeline, like analysts or scientists, to use it and further enable kind of machine learning workloads, BI workloads, any kind of analytical workload. So data warehouse or kind of, in a more technical sense, OLAP databases were kind of the first one to enable this, right? But then it lacked the abilities to deal with unstructured data for more advanced use cases such as machine learning. Um, that's kind of a shorter version. Of course, like, there are like other aspects to consider and, they're really good with relational workloads and structured workloads. But then with the rise of like, Hadoop ecosystem, the era of data lakes, we were primarily dealing with the problem of kind of a variety of data types. And data lakes were kind of great, right? Organizations could basically store all of their data, whether it's structured, semi-structured, unstructured, it doesn't matter in a data lake system. Most importantly, it started with something like a Hadoop distributed file system, which kind of gave a way to that. And then with the rise of cloud and its kind of cheaper cost, we now have the cloud data lake storages, such as Azure Blob Storage, Amazon S3, all the three major cloud vendors. So you can basically scale out storage as you would like. But of course, the cost is also a huge impact here. That over the years, we have realized it to be really good in terms of the newer problems that we are addressing. But of course, there were a couple of kind of caveats or problems, and that's how we kind of ended up with the lakehouse architecture as well. So one is you just can't dump all of your data and let your analyst or scientist deal with the physically stored data, right? So if you wanted to do BI, which is a very common workload, you still needed to organize the data and you want to get it out in a more of a structured form. So you still need a data warehouse to do that. And then you can do your reporting, BI reports on top of that. And the most important problem was that data lakes, they kind of lack those atomicity and consistency guarantees, right, with transactional workloads. So for example, things like updates, deletes, record level updates. It's hard to do ACID-based transaction. How many times have you seen like, two jobs writing at the same time at the same kind of data set, and you end up with either partial writes or kind of zombie data, which is like really unexpected. So it kind of like this long running job, takes a while, but then you lack those guarantees, which kind of end up with a lot of like engineering efforts, cost efforts, and it's kind of cumbersome to deal with. And most importantly, it was also really hard to get, kind of make sense of all of the data, right? Because there is no real governance or kind of data quality checks around that. Although, there are some ways to do that, but it was not more streamlined, I would say. And it's hard, right, to just make sense of a machine learning model, which is basically trained on such a data, or even like a BI dashboard with some key performance indicators. How can you really trust on that data when you have those data quality checks or guarantees are missing? So these kind of gave rise to a new architectural platform called Lakehouse, and of course that doesn't mean we don't need a data warehouse or data lake today. Data Lakehouse addresses some of the pressing challenges that have been seen with this two different architectural form, and it kind of provides a different or a better way, I would say, to handle some of the modern workloads that we are seeing, specifically things like streaming, more of a unified platform, and those kind of things. So what's a lakehouse? And it might be pretty common for people, and you might guess from the name itself, it's combination of a data lake and a warehouse. That's kind of the most like canonical jargon. But of course, this is not just a mere combination of the two kind of architectural patterns, but the whole idea is to take the best of the both world. For instance, data warehouses, like they have great data management capabilities, right? Great optimization capabilities, things like compaction, clustering, ability to do things like time travel, which is really important for some business use cases, schema evolution. We have changing requirements every now and then. How do we kind of evolve to this requirement? And of course, like transactional part is a huge aspect, right? Those ACID guarantees are really good with like data warehouses that we have seen until now. And then data lakes, on the other hand, they provided the scalability option, right? We touched a little bit about it. Um, and you are allowed to elastically scale as you would like, to unlimited kind of like infinite scalability. And of course, the cost factor is a huge consideration for organizations who are dealing with kind of this larger workloads, or multiple kind of workloads. So lakehouse basically builds on this idea, and the most important thing kind of that lays the foundation for a lakehouse is the table format, which is also one of our focus, and how we are coming to like XTable today. So just a quick like summary of the different components that are involved, and I'll just point out some of the major like highlight to take away from the slide itself. And I'll start from the bottom to the up, like that. So if you see in the top, in the bottom part, you see the cloud data lake storage, right? This is where your data lands from, ingestion from various operational system, like whether it's a CRM system, any kind of relational databases. You basically ingest the data into this any kind of major vendors like S3, Azure Blob, or Google Cloud, or even like a on-premise file system like Hadoop file system, right? So they support storing any type of data. That's the best part. The variety is there, and of course, it provides the required like performance, the security aspects of it, super important governance and everything. So that's the data cloud storage there. And then we have the file format on top of that. And this is where your actual, like the bytes are written to the formats itself, right? And basically the file formats define how you're writing the data in a particular way, whether it's, in a row-based fashion, whether it's a columnar fashion, depending on our use cases. For example, like columnar-based workloads, columnar-based file formats, they're really good for analytical side workloads, right? They have greater performance optimization capabilities, like for example, Parquet, really good with like rich metadata support, and you can use it to like prune your like data files. So that's really great. And on the other hand, maybe row-based formats like Avro are good with like write-heavy workloads, right? Append-only workloads, super important. And if you see the layer on top of that, you can see the transactional layer, which is basically what makes up the lakehouse, right? All this while, the transactional layer is actually what was missing in this data lake that we have seen in the storage layers. And of course, the main important thing, of course, is the table format that kind of brings this kind of guarantees and the ability to like abstract the physical data structures complexity, right? So you see this table format a layer above the file format. So basically, the major kind of like the file format like Parquet, ORC, Avro, whatever it is, it's a layer on top of that. So Apache Hudi, Iceberg, and Delta Lake are the three popular table formats that we see today. And obviously they have widely gained enterprise adoption today. We're seeing more of it happening now with more workloads. But of course, in the past, we have had a common one. Everyone, pretty much all the big data folks have worked in the Hive table format. Um, and Hive kind of led to the inception of like certain of the table formats like Iceberg for that matter as well. Uh, and then we have the compute engines and the downstream app that you see on top of the entire like the transactional layer stack. And basically, these are the query engines who are like crunching the data, doing the transformation, and things like it can be anything like whether it's Spark for distributed ETL, Flink for real time, any other data warehouse-based compute engine, OLAP databases, whatever it is. So one question that always came to my mind when understanding a lakehouse architecture was kind of how I compare this with like an existing transactional architecture, like a database or like a data warehouse, right? Which is more of a OLAP database. So the main thing to take away from here is that the distinction between a data warehouse architecture and something like this is that in a lakehouse, each of these components that you see, they are not bundled up into one single system, right? Whereas in a data warehouse, you will see pretty much like all the system, pretty much all of this component that you see, they're also present in a database or a data warehouse. For example, the file format itself is proprietary, or maybe the table format is specific to the particular vendor system. But overall, we have been calling the table format storage format for years now, right? I mean, with database system. So basically, it kind of builds up on that. And the interesting thing to note about that is that the lakehouse architecture is very modular. So that gives you an ability to mix and match different things. So your table format and file format itself, which is the main kind of like the data tier, it sits as an independent data tier and it's open. That means you can bring your compute engine depending on your workload to that particular data, rather than going the other way around where we used to bring the data itself to the compute engine. So it's kind of a different approach in a way. But the fundamentals are still the same. So it's not a new thing in a new way. It's just a way of different in a different way of doing things. If you're interested in learning a little bit more, there's there's so many papers out there, so many interesting blogs. But I personally picked up the Lakehouse blog by Databreaks, and I also published a paper some time back during my time at my previous job. So these are just a good comparison to understand between the data lakes, data warehouse, and all those kind of nitty-gritties. So coming to our focus, table format. So usually with databases, we have seen the concept of table. Like I said, it's not a new concept at all. Like, they are basically what loosely the databases have been referred to as storage format for over the years. Companies such as Oracle, Microsoft, they have been doing that with relational databases for some time now. So basically, it's a way to organize a dataset's file to present them as a single table. So users don't really have to know about the physical bytes and files, and they can just have that abstraction on top of that, right? And like I said, with the big data world and Hadoop and HDFS, we ended up with the Hive, right, as a query engine. So more people can have access to data, which was previously limited to just, engineers specialized in MapReduce and, more of that kind of skill set. They didn't have a way to, like data analysts, for example, like in my previous organization, they didn't have a way to access the data that was sitting in the data lake, although they could make a lot of sense out of that. So Hive QL or, Hive query language, pretty similar to SQL that came up at that point of time. It provided a way to like democratize and provide more users with more access of data. But of course, we needed also schema around that and how we kind of refer to that schema as a table. So that's when the Hive table format came into the picture. People usually get confused between the Hive table format and the query engine. It can be a nebulous term in a way. So it's important to understand the table format itself is a different one. And as an example, I just laid it out before we even go to the modern table formats. But basically what you see here is a folder structure. And within the folder, you have the different files, the data files itself, and that folder itself represents a kind of table in the Hive table format. All right, so like I said, that's kind of the inception, and that's kind of like the segue to even like, the different table formats that we see today. And a lot of inspiration has been from there. But let's quickly take a bird's eye view into today's modern table formats like Iceberg, Hudi, and Delta. And basically a one-liner is that they are kind of a metadata abstraction. And in a more generic sense, it would just be the metadata files that you see on top of the object storage. So how the metadata files are organized and designed are a bit different for all of these three different formats. But the overall idea is the same. Delta Lake does that with a JSON-based transaction log, right? It keeps a track of all the transaction. Iceberg uses a bunch of metadata file and manifest file, and it keeps a track of the data files based on a reference implementation on the catalog. And Hudi takes a timeline and indexing-based approach. So the way it is done, it's a bit different, but overall goal and motivation is basically the same. And once you create a metadata abstraction on top of the file storage, then you can explore foundational characteristics, right? For example, like table and SQL semantics that we talked about, something very common to analytical world, right? And capabilities like schema evolution, like which is very common in like data warehouses. And because of the data files, the nature of the data files itself is immutable, right, in nature. So having the metadata layer on top of that, it enables those ACID-based guarantees of transaction, and you can do updates and deletes and those kind of things. Now, apart from the metadata layer itself, you can obviously see the other highlighted components over here as well. There is the catalog layer, which is super important, and we are seeing more of the importance now. It basically, has the concurrency aspects, the governance aspect to it, and how it kind of collates all these different tables that are sitting in your organization. But of course, like data layer is also super important for your performance perspective, the cost factors, and how you can take benefits of some of the optimizations from here. So all of this different layer has a combined effect on the end-to-end performance and the behavior of your, architecture. So coming to the main point, the thing is fundamentally these three table formats are not much different. Like I said, when data is kind of written to the data distributed file system, these three formats have similar structure, right? And the metadata layer, they impact the quality plan and the query planning. And the most important thing to note of this is that although, like I said, the goal is the kind of same and the structure is different, the metadata still shares a lot of similarity and is something that we can work on based for our next, kind of Lakehouse 2.0 or the interoperability factors that we are seeing more now. So this is just a kind of a high level picture of what you would typically see in like a table format metadata layer. Just to show you like that table format, like the term can be very confusing sometimes. So people ask like, what exactly is a table format, right? What do you see? What exactly is the content of the table format? So this is what you typically would see across the three table formats, right? Whether it's a data and delete file information, the list of the path that are relating to the data files, specifically for like things like Iceberg, schema information, right? The structure of the table, column names, partition information, statistical information, super important, right? The min and max values of the Parquet file, the row value counts. So these are all the information that you are collated into this particular metadata layer, which kind of gives us to what we're looking for. So that brings us to kind of the question, right, of the hour, which is which format should you choose, right? And this is probably one of the most common questions that you will end up getting when you are either like deciding on like implementing architecture for yourself, whether you're a vendor who are deciding between formats for a specific format support, or even things like interoperability, right? And to be honest, this is a tough question, right? Everyone's workload, use cases, ecosystem are a bit different. And there are so many factors to consider, honestly. So it is really a difficult thing to like compare and choose. You will see a lot of comparison articles, but to be honest, it really comes down to like a particular use case. Overall, how it comes down to is basically like feature level comparison. Like for example, like we might be looking at if a particular table format has a merge on read support, right, for streaming based use cases. If so, if there is an optimized way to like even like do some trade-offs between latency and freshness, right? So these are the things you might do a like comparison. Of course, complexity of implementation is also a super important thing. Personally, I have helped a lot of like, organizations like productionized lakehouses, and a lot of learning has been that there is a curve towards like, implementing something. So how easy it is, for example, you might be in a high-based ecosystem today. Should I move to Iceberg today or Hudis today or, Delta? It really depends, right? Ecosystem support is another very important factor, right? Community support. These are all open table formats. That means community is a strong presence, and you need that as a community to grow the format, the ecosystem as well. And on top of that, there are also some new challenges that we are learning, right? For example, there are teams that are organizations that are operating multiple table formats in production environment, and the reason is like they are different teams within the organization who are dealing with different challenges, different workloads, right? But now it has come to a point where they want to make a sense of all of these different table formats and see if there is a way to like interoperate between them and bring together all these different sources together. So the question really comes down to, do we have to choose, or is there any other way, or what if you could use all three, right? So usually when I pose this question around using multiple table formats, people ask, oh, why do we even need that, right? Why is there a need to use multiple table format? Which is I feel it's justifiable, like in a way, like depending on if you're a team which is particularly focused on one particular use case. So what it comes down basically is like in experiences, these are of course experiences like working with different customers, different users, is that the overall lakehouse paradigm, the organizers wants to be more interoperable. With the flexibility of having that open and independent data tier, they want to see if they can interoperate between these different data tiers as a whole, right? And if there is a need, for example, like today I'm using Spark for my distributed ETL, tomorrow I could just rely on a different compute engine as a whole. Or for that matter, if I'm using like, by choice of catalog for that matter, right? It can really vary and it can really depending on the feature comparison or whatnot. So I'm not limited today to like use to one particular thing, whereas I have the ability to mix and match different things. So here are just quick some examples like and more of learnings like based on what we have learned from the field is why you need kind of mix and match architecture, right? So basically, you might have certain teams who are relying on a particular table format. So for example, you start with, let's say, Iceberg on BigQuery. That's the table formats which optimize for writes. But on the read side, you might want to choose something like, Delta Lake with Databricks. Maybe you are in Databricks ecosystem. The other set of people, they might be using, Delta Lake with Databricks, which works really well. Or similarly, Delta Lake is kind of the kind of default with like easy to get started with Fabric ecosystem. Maybe on the read side, you want to use like Dataproc or Spark with Hudi. So these are the different kind of like set of examples that we have seen people using. And you can see there are like some common patterns, right? It is also really kind of like correlated to the ecosystem and the support of a query engine. Because it's really hard, like for a particular particular vendor or a query engine vendor to really open up and optimize these capabilities for each and every format, which realistically, in a more like holistic sense, it makes sense. But if you have to do it for every single format, it kind of becomes a more challenge in terms of product and roadmap growth. All right, so we have seen the problem now, and I took a little bit of time on this, but our solution, which is XTable, and it's an open source project that allows you to achieve interoperability between these three different table formats. And of course, it's not limited to just three table formats. We also see some new formats coming in, like Pymon, for example, for Flink. So it can easily be extended by implementing an interface in a more technical sense. So the idea with XTable is pretty much simple. You write once and you query everywhere. And it provides flexibility for different teams to choose and cater to these different use cases. So a little bit of more context here. XTable provides omni-directional interoperability. The reason I'm kind of like choosing the word omni-direction is because there are different ways to convert from one table format to other. Whether it's a one-off migration strategy, whether it's like, for example, the Iceberg project allows you to do like a snapshot-based migration, right? You can just do a one-off migration to Delta. But with XTable, the idea is that you can initiate conversion from any format and you can just go around, there is no need to rewrite or copy data in that sense. And also, it's important to understand, people ask like whether XTable is like a new or separate, completely different table format. It is not. Instead, it's just a set of abstraction and tools which are designed to like just work on the metadata part, and we are not even touching the data. So the overall goal, like I said, with XTable is that you can start with any table format of your choice. And if there is a specific requirement in your organization to like switch and use a different one on the read side or the write side, you are free to do so. You are not limited now, right? So all you have to do is basically it's a YAML file. So you have to just specify your source, you specify your destination, and XTable will do the translation of the metadata layer. At a high level, this is what the XTable architecture looks like. This is from a paper that Ashvin and team also published. So I'm not going to go too deep on the details. I might just link the paper source for the readers to like go over the paper as well. But in a more high-level sense, there are three components here. There is the conversion source, the target itself, and the conversion logic. So the conversion source, just to quickly walk through, these are kind of table format specific modules. They're basically like taking a source format's metadata and they're trying to read it. For example, things like schema-based information, like transactional information, partition-based information, and they're trying to translate into XTable's unified internal representation. The second part is the conversion target, which basically is on the right side, right? You take a source format and you kind of like mirror that same thing, and you take the internal representation that you did from the source reader side, and you map it to the target format's metadata structure. Because, like I said, the metadata structure is a bit different for different ones. So basically, you do the mapping. And the last part is basically kind of the central processing unit of the XTable, and it kind of tackles all the major tasks, like whether it's like keeping it, track of the state, translation process itself, caching and efficiency and this kind of things. So that is pretty much all that I had. I'm going to hand over to Ashwin, where we are going to learn a little bit more on the practice side and think and apply those theory that we kind of learned today. All right, Ashwin, I'm going to stop sharing, and it's for you to take.
Can you see my screen?
I can see your screen.
Okay. Hello, everyone, and thanks, Dipankar. That was a very insightful introduction and a comprehensive overview of XTable. And as Dipankar mentioned, next I'll talk about some of the practice, XTable in practice and the adoption, how it has moved forward, and get you introduced to some of those things. So, a quick recap of what Dipankar just presented. And XTable is an Apache project. And what it means is that it lives by the Apache Software Foundation principles. It ensures transparency, and it is a community-driven development project. Right. Currently, XTable supports interoperability between Delta Lake, Iceberg, and Hudi. What it means is that users write their data once and they are able to read their data in any other format, essentially by replicating just the metadata of the tables. So it supports those right now, and then it is extensible. What it means is that tomorrow, if new table formats or specialized table formats emerge, we will be able to add those. Or if there are new features required, Xtable will has it is designed to support extensibility. One of the most important things which we cannot repeat enough is that the data which is in some Parquet files or RC files, that is not replicated. There's a single copy of the data. It's a metadata, which is a small volume of the total table size. That is what we replicate. So single copy of the data is a important principle here. And also, it's not that we convert once and it's done. Xtable provides incremental synchronization. What it means is that if a writer updates the table data, then only that increment metadata is what is also mirrored on the target side, which means that on the readers, you will always get the up-to-date copy of the table format. So all this is good, right? Is Xtable ready for production deployment? That is the burning question, and the answer is yes, of course. Let me provide you some more background on that. In the industry, the popular norm is interoperability on single table format. What it means is that multiple compute engines, which are specialized to perform specific to solve business needs, they will all read the same table format, perhaps the same file format also. And in many cases, they also agree on, they standardize on the data encoding, the column types. There's a preferred list, and that is what is the industry norm. And this, the reason is because it simplifies a lot of things. It is easier to maintain the code, and there's a lot of guarantees which can be provided. For example, Microsoft is one of those in the trend, and it features a compute layer and a storage layer. The compute layer consists of various specialized compute engines which are tailored to meet specific business needs, and a storage layer which is called One Lake, which provides a unified storage solution, which Dipankar mentioned earlier. So the important thing to notice here is that all compute engines in Fabric, they store data in one lake, and they all operate on the same copy of the data. So there is data is never duplicated. All the engines, because all of them understand one table format, they are able to read and use that data. This table format is Delta Parquet format, and I'll explain more later. But the important thing is that each of these engines not only is able to read the data, but it is also optimized to work with this format, and it directly reads from the lake underlying lake. So there's, again, to reiterate, there's single copy of data, and all compute engines, the can users based on the need, they all will be able to read the data of all the tables which are in the one lake. And the format there is called Delta Parquet. So Fabric ensures that the data is seamlessly interoperable between these engines, and various business use case applications can be supported because of this unification. And if you noticed earlier, instead of calling Delta Lake, I was calling it Delta Parquet. The reason is that the data, which is in the columnar representation, is always in the Parquet file format, and the table evolution, the schema, the metadata of the table, essentially, that is represented, that is published in the Delta Lake format. That's why I've been calling it Delta Parquet format here, because as Dipankar mentioned earlier, these are two different layers in the table format stack. Going forward, what Microsoft has announced is that in addition to the Delta Parquet, it will also support the Iceberg format as well. Like Delta Lake, Iceberg also has a metadata layer, and it supports Parquet files for the file format. And what it means is that if the data is always represented in the Parquet file format, Fabric engines can read those. And if Fabric is able to generate the delta data for that, it can operate across the storage formats and the table format and provide a unified data management layer over a single copy of data, which is in Parquet format. And with no surprise, the interoperability across table formats in Fabric, it will be enabled through the integration with XTable. So that is the part which I was talking about. XTable is now getting deployed at scale. And what is what this enables, this Iceberg integration, is engine level interoperability across different organizations. So Snowflake, this is also a recent announcement. Snowflake was it primarily operates on the Iceberg file format, and by adding support for Iceberg in Fabric, now it can easily interop with Snowflake engine. So internally, XTable would convert between Delta Lake and Iceberg metadata seamlessly in both directions, which means that Snowflake can read Fabric data and Fabric can read Snowflake data. And what is the most important thing here is that in either side, there was on the engines, there was not a single line of code change required. Both the engines, they continue to read the format which they support, which they're optimized for. But Xtable transparently mirrors the metadata of the table format without copying the data, and this enables the interop across table formats and interop across these engines from different organizations. So what it brings is that there are no data silos now. Even if users want to use different table formats, different engines from different organizations, they can integrate and they can get a unified view of their data estate. And as it is clear, there is no data duplication here. The platform ensures that the single source of truth for data, and which all eliminates inconsistencies and errors. Data remains in one place. There is no need to copy the data or move the data across data lakes, across clouds, which is obviously costly and time consuming. The platform also ensures that the data is up to date. As I mentioned earlier, with Xtable, I can do incremental update. The Fabric integration allows that the data, as it takes whenever the data changes in one table format, and it automatically invokes Xtable to produce data in the other table format. That way, both the engines from wherever the user is invoking it get an up to date and real time information of the table. So with the final and the most important thing is that this integration is actually transparent to the user. The Fabric integration takes care of invoking Xtable for mirroring the metadata. The user, there's no user action required as such on a regular basis. It's a one-time setup, and whenever the Xtable integration is enabled, the replication happens internally. So with this integration, what we will know is that Xtable will be used by thousands of users at scale for maybe tens of thousands of tables and at all replicating at the same time. So this is the powerful feature which is now enabled by Xtable. And having said that, there are a lot of cases still which need to be developed. There are a lot of features which have to be implemented, performance and so on. And we obviously invite you all to join the community to learn from us, to share what your use cases and collaborate with us. And our main goal is to unlock the true potential of data. With that, thank you.
Thank you so much, Ashwin. Yeah. We'll take any questions that you might have now. Yeah, thanks.